Now we will be discussing AVL trees. AVL tree is a self-balancing binary search tree in which the condition is that the difference of heights between the left and right subtrees is always at most 1. Now first we have to see why we require an AVL tree. For that we have to look into the limitations of a binary search tree. Binary search tree has O of H, insertion and deletion. But the problem with this is that in the worst case a binary search tree can be as worse as O of N. The height can be as worse as O of N for a skewed binary tree. That's why we require balanced trees such that our search is always order of log n. To ensure that we need balanced trees, and that is where AVL tree comes into the picture. In AVL tree, what we do is that because of these conditions where the height is at most 1, we ensure that the height has maximum floor of 1.4 for log n. For AVL trees, this ensures that since the search is order of H, your search will always be O of log n. That's why AVL trees are much better than binary search trees, even in worst cases. So, first for AVL tree, now search is like normal BST, so we'll see insertion in AVL trees. For insertion, we have to learn rotation. That after first we'll do normal BST insertion as we do in normal binary search tree. After that, if our tree will be unbalanced, then we have to perform restructuring to ensure that the property of AVL tree is still satisfied. What we do here is, let's say this was our first tree, means initial tree, and if we have to right rotate it from here, then our tree becomes like this. X goes up, it comes down here, X, Y, the right child of X, now right child of Y becomes Y, so T2 goes, becomes the left child of Y. This is right rotate, left rotate is the opposite of this. So now we'll see the steps to perform while performing insertion in AVL tree. Let's say V is the node to be inserted. So first perform standard BST insert for V. After that, travel up from V and find the first unbalanced node. To do this, what we can do is that for every unbalanced node, we'll find an index that sees whether it's balanced or not. For balance, we have to find height of left tree minus height of right tree. Height of left minus height of right. It should be either 0, 1 or minus 1. That's the condition of balanced. If not, then it's unbalanced. So go travel and find the first unbalanced node and call it Z. Now while traveling, let's say Y be the child and X is the grandchild of Z that we go through when traveling from V to Z. So now we have the cases. Since we have to balance our tree, first is the left case, that Y is the left child of Z, X is the left child of Y. Then simply right rotate Z. T4, T3, T2 and T1 are subtrees. So this will become Y goes up, X, Z, T1, T2, T3, T4, and now it has become balanced. Now all the nodes have become balanced. The other case that arises is the left-right case, where Y is the left child of Z, X is the right child of Y. In this case, we have to perform two rotations. The first is that we left rotate Y to ensure that X goes up, T2, T1, T3, and then again right rotate Z. This comes down X, Y, Z, T3, T1, T2, T4. The right case is just the mirror of left case. We only have to perform one left rotate Z. Right case is the mirror of left case. We have to perform right rotate Y. After that, left rotate Z. So let's just see an example. Let's say this is our AVL tree. These numbers are just the height of left tree minus the height of right tree. Here the height of left tree is 1, 2, 3. Height of right tree is 2. So this is plus 1. So we can see all are 0, minus 1 or plus 1. It is balanced. Let's say we have to insert 7 into this tree. So first we perform standard BST insertion. 13, left 7 is less than 13, 10, 7 is less than 10, left 5, 7 is greater than 5, right 6, 7 is greater than 6, right 7. So we insert 7 here. And now when we calculate, we see that some nodes have become unbalanced. So we go travel up from 7 till the first unbalanced node. 7, 6, 5, 10. 10 is the first unbalanced node that we recur. So now we have to see the condition. 10 is Z, 5 is our Y, this is X. So this is the left-right case. In a left-right case, first we'll left rotate 5 to get this, then we'll right rotate 10. In the final tree, we can see all the nodes are balanced.